So now we're going to be looking at trying to find the largest or smallest values of some function on some interval. So to start off with, let's consider kind of an easy example. Let's say we're looking at the graph of this function right here. This is some f of x. The values of it go on the x-axis from 0 to 7, and the y values go from -1 to 3. So if we wanted to look at where the maximum value of the function was, that would be here. The maximum value of the function is going to be the y value portion. So here that maximum y value is going to be 3. Now we want to know where that maximum occurs. So when we're saying where does it occur, we're talking about what the x value is. So here we'd say that x equals 2. So we got the point 2, 3 up here. That is the highest value for our y values. So that's where the maximum occurs. Next we're asking where the minimum value occurs, and that would be right here. So here we'd be saying, we're talking about the value specifically, we're talking about the y value. So in this case, it'll be -1. And if we're asking where the minimum value occurs, that's going to be the x value where we get that. So that would be x equals 6. So if we think about what's happening at these points, at the maximum, we have a horizontal tangent line. And at the minimum, we have something where it's not differentiable. So at max, the derivative is equal to 0, and at minimum, the derivative does not exist. Okay, so why do I bother bringing this up? Well, we're going to actually be able to use our derivatives in order to help us determine where our maximum and minimum values are for some function over an interval. So a couple of places of new terminology. A number c is going to be called a critical point if two things. One, c is in the domain of the function f, and two, either f prime of c equals 0, or, make that a little better, or the derivative at c does not exist. So these will be what these critical points are kind of referring. If we say the word critical point, this is what we're referring to. It has to be in the domain of the function f, and it has to either have a derivative of 0 or a derivative that doesn't exist. On this graph above, our critical points are x equals 2 and x equals 6. So here the c is referring to an x value. So above x equals 2 and x equals 6 are critical points. Extreme values of the function f of x on an interval are the absolute minimum and absolute maximum values of f of x on the interval a to b. So this is going to be the y values. So here, these are y values. And this is the absolute minimum and technically these are y values, absolute maximum, values of f of x in the interval a, b. And so above, we would have had 3 equals the absolute max, and -1 equals the absolute min. Alright, so the reason we say absolute here is these values are ones that were above any other or below any other y that we were looking at. So here this 3 is higher than any other y value in the entire graph, and for -1 it was lower than every other y value in the entire graph. Now we also can have what are known as local maximums and local minimums. So a local max is something where f of c is greater than or equal to f of x for input x nearby c. So in other words, we're saying if it's higher than all the things around that part of the function, then it would be considered a local max. Whereas a local minimum, f of c, would be if we had some f of c that was less than or equal to f of x for input x values that were nearby c. So say that we had the graph of some function and it was a little bit wavy. Okay, that is only kind of okay drawn. Let me see if I can't pull that out a little more. So anywhere where we have kind of a low point amongst all the things around it would be a local minimum. So we'd have a local minimum over here, over here, over here, and over here. So these would all be local mins. Whereas all these high points that we have would count as local maxes. Now note that our absolute minimum or absolute maximum, these highest and lowest points, would still be considered local mins and maxes, but they would also be considered absolute mins and maxes. So what we're going to do is we're going to take a look at first just making sure we can find our critical points, and then making sure we can find these exact these absolute mins and absolute maxes. So first we want to make sure that we've got the domain that we're looking at. So we're going to find all critical points of this function h of x, which is x to the 3/5 times 4 minus x. So first thing to do is to check our domain. So do we have any square roots to deal with? Nope. Do we have any even roots to deal with? Again, you have to check for a second, but if we're making it 3/5, the 5 is something that's odd. So our domain for h of x is -infinity to infinity. We could plug in whatever value we want for x, and that'll be fine. Now we can use either the product rule or distribute the x to the 3/5 and then take the derivative. This will be good practice in case we're still struggling with the derivative a little bit. h prime of x in this case will be negative x to the 3/5 plus 3 times 4 minus x over 5x to the 2/5. So when we're trying to look for our critical points, we want to know where the derivative equals 0 and we want to know where the derivative does not exist. So again, critical points are looking for the x values here. So the first thing we're going to do is we're going to take the derivative and set it equal to 0. So this will be negative x to the 3/5 plus 3 times 4 minus x over 5x to the 2/5 equals 0. If we rearrange this, so in rearranging, I'm going to go ahead and distribute this 3 finally. We'll get 12 minus 3x over 5x to the 2/5 equals x to the 3/5. So we'll go ahead and add x to the 3/5 over to both sides. Now from here we can go ahead and multiply 5x to the 2/2 over here. And what we'll get when we do this is 12 minus 3x equals 5x. So x to the 2/5 times x to the 3/5 is going to give us x to the first because we add those exponents together. Now from here we can go ahead and rearrange this a little bit further, add that 3x over to the other side, and we'll get 12 equals 8x, and then dividing will give us that one of our critical points is x equals 12 over 8, or just 3/2 when we reduce. So this is one of our critical points. Our other critical point will come from when the derivative doesn't exist. So when will this not exist? And the answer is whenever we break its domain. So we don't have an even root to worry about. However, we do have something where we've got something that could be 0 in the denominator. And so if we set 5x to the 2/5 equals 0, we'll see that at x equals 0, the derivative does not exist. So x equals 3/2 and x equals 0 are our critical points. Now from here, what we'd be able to do is we'd be able to plug these back into our function in order to try to find our mins and maxes. We'd also have a little bit of extra stuff to do based on what we decided to make the interval we were looking at, but we'll get into finding those a little bit later. We'll do one more example first of trying to find these critical points. So let's say we've got the function here g of x, where it's equal to 1 over x minus 1 minus 1 over x. Now here, our domain for g of x is going to be negative infinity to 0, union with 0 to 1, union with 1 to infinity. So in other words, we cannot have 0 or 1 at all be input into our function. So we'll have to keep this in mind, because if we find that some of our alleged critical points are 0 or 1, they won't be critical points because of what we have to do with that and what that means. Because if it's not in our domain, it's not allowed to be a critical point. So if we want to take the derivative of this, we can think of g of x as being x minus 1 to the negative 1 minus x to the negative 1. Now this is something we can use the power rule on, and this is something that we could use the chain rule on. So I'll let you guys either discuss on the discussion boards or try for yourselves to see if you can get this chain rule. But what you should get for g prime of x, by the time you're done with the chain rule, is negative x minus 1 to the negative 2 plus x to the negative 2. Or we can rewrite this as being negative 1 over x minus 1 squared plus 1 over x squared. Alright, so we have two cases we have to worry about. We have to worry about when g prime equals 0 and when g prime does not exist. So let's worry about that equals 0 first. So first we'll take negative 1 over x minus 1 squared plus 1 over x squared, set it equals 0. Since this is negative, we'll go ahead and add it to the other side. We'll end up with 1 over x squared equals 1 over x minus 1 squared. If we multiply both sides by x minus 1 squared and by x squared, what we'll end up getting is x minus 1 squared equals x squared. And so if we rewrite the left-hand side by foiling it out, we'll get x squared minus 2x plus 1 equals x squared. Subtracting over x squared on both sides. Okay, there it is. Looks like my camera froze for a second. We'll get negative 2x plus 1 equals 0. And then rewriting this, we will get 1 equals 2x, which tells us that x equals 1/2 is a critical point. Now note, this is in the domain, so it's allowed to be a critical point. So this will be one of our critical points. Next, we want to go ahead and look at where g prime doesn't exist. So, if we take a look here, again, our denominators will have issues when x is 0 and x is 1. So, x equals 0 and 1 would be potential critical points. However, these are not in the domain of g of x, so they are not critical points. So this x equals 1/2 then is our only critical point. So that's the only one we have for this function. Okay, so let's go ahead and look at another graph and say that we wanted to consider the graph of this function on 0 to 10. If we wanted to look at the absolute maximum and absolute minimum of the graph on this interval, remember these absolute mins and maxes are called extreme values, and these are the y values that we're looking at. So when we take a look here, this is our lowest y value, so this will be the absolute min. And here, this is our highest y value, so this will be the absolute max. So again, these are the y values that we're looking at. So for the absolute min, we'll have -3 as our value, and for our absolute max, we will have 4 as our y value. When we ask where the extreme values occur, these are asking about the x values. So the absolute min occurs at x equals 0, whereas the absolute max occurs at x equals 5. So that's where the x value is for the absolute min, that's where the x value is for the absolute max. If we wanted to know where the derivative was 0, we'd be looking for these horizontal tangent lines. So the derivative will be 0, where we have a horizontal tangent here at x equals 3. Also up here at x equals 5. And is there anywhere else we can see? Looks like it also might be 0 here at x equals 7. Now we also want to think about if there's any places where the derivative is undefined. So we want to be looking for these potential things that our critical points would be. And so here, remember when we have any sharp corners like this, the derivative will be undefined. So x equals 2 will be a place. And if we ever have a vertical tangent line, like we might have at x equals 8, that would be another place the derivative is undefined. So then our critical points, remember, are any places where the derivative is 0 or undefined. So these will be x equals 2, 3, 5, 7, and 8. Now something worth noting is that except for when x equals 8, most of the rest of these places are where we have local mins and maxes. So this is a local max at x equals 2. At x equals 3, we have a local min. At 5, this is an absolute max, but it's also a local max. Here at 7, we have a horizontal tangent line, so not quite a min or max. Here we have a vertical tangent line, so again, derivative does not exist, don't end up with a local min or max. We also have, on the endpoints, a few one-sided local mins. So these are we say one-sided because we're not looking at our function on both sides. So some individuals will consider one-sided local mins and maxes to not be mins and maxes at all, and others will. So one thing that is worth noting about where we have these mins and maxes is where they occur. So the different types of x values we can have that give us a local max are either critical points or endpoints of an interval. Now, as far as places that could give us then our extreme values, those mins or maxes, we're looking at the same thing. We're either looking at critical points or endpoints. So note that just because you have a critical point does not mean you will get a local min or max. So in the previous example, x equals 7 and 8 in the previous example. And this theorem here will kind of sum up so far what we have. So the extreme value theorem says a continuous function on a closed interval, so you can think of this as being some a to b with the endpoints included, has an absolute minimum and an absolute maximum value. Furthermore, these extreme values must occur at critical points or endpoints. So Part of the reason we need to have a closed interval is that they only can guarantee the absolute min or max if we restrict our interval and include endpoints. And it kind of pins down the graph so that it can't go to infinity or negative infinity. As you kind of see a visual representation of this, say we were looking at something where the graph looked as follows. So we've got an open circle here, and it's increasing the entire time. And we've got an open circle here. Now we can get as close to whatever this value is as we'd like, but we'll never actually reach what the true maximum is, the absolute maximum. And here we can get as close to the minimum as we'd like, but we'll never actually reach either of these values. So this is something where if we don't have a closed interval, we can end up with a funky corner cases where we don't have any sort of endpoints that we can look at, and that causes some issues for us. All right, so let's say we wanted to go ahead and kind of summarize our steps for finding these extreme values. So first and foremost, we have to find the critical points of the function. And how we do that is we find the derivative and figure out what x values have the derivative equal to 0 or the derivative be undefined. From here, we'll go ahead and make a table of values that have a column for x and a column for the function f of x. In the x column, we're going to list our critical points and our endpoints. And then we'll go ahead and plug all these values in to the function. Whichever one gives us our largest value is the absolute max, and whatever gives us our smallest value is the absolute min. Okay, so let's say we want to go ahead and do this with an example. So we want to find the exact absolute min and max values of f of x equals x minus 2 sine of x over the interval 0 to 2 pi. So just some notes here. The interval is 0 to 2 pi. The domain of this function, for when we try to find our critical points, is going to be negative infinity to infinity. You can take whatever you'd like and plug it into the sign. Now the derivative of f of x will be 1 minus 2 cosine of x. So the derivative exists everywhere, so we don't need to worry about the case where it does not exist, because you can plug whatever value you'd like into cosine. So now we want to figure out where f prime of x equals 0. And so that means that we set 1 minus 2 cosine of x equal to 0. If we move over the 2 cosine, we'll get 1 equals 2 cosine of x. And this means that we're looking for where cosine of x equals 1 over 2. Now, what you might know about sine and cosine is that they are periodic functions. So what that means is that there's an infinite number of places where cosine will be equal to 1/2. However, we're only looking at the interval from 0 to 2 pi. So because of this, we can use our unit circle to figure out where the cosine equals 1/2. And so this, on that interval, will be pi over 3 and 5 pi over 3. Again, this is something where you can find with your unit circle. So if you don't remember how to do these inverses and figure out where our values for cosine equal 1/2 are, this, going back to looking at a unit circle, will be very helpful. So these will be our critical points. We don't have any others to look at because, again, our derivative exists everywhere. So to find our absolute min and max, we have to go ahead and create a table that has our critical points, our endpoints of the interval, and what their function values are. So if we plugged in pi over 3, I'll just write them all out. So pi over 3, 5 pi over 3, 0, and 2 pi are the different places that we have to look at. So these are the endpoints of our interval, and these are our critical points. So if we want to find f of x, that's f of pi over 3, which is pi over 3 minus 2 sine of pi over 3, which is roughly going to be negative 0.68. Next we'll have f of 5 pi over 3. So notice that when we're doing these, we're using the original function now. So keep that in mind. We'll get 5 pi over 3 minus 2 sine of 5 pi over 3. And you should get roughly 6.96. Again, something to make sure you're doing with your calculator is making sure you are using radians and not degrees. If you're using degrees, you will not be getting the same answers that I am. And because we don't specifically call it degrees, we are working with radians. If we plugged in 0, we'd have 0 minus 2 sine of 0, which will just be 0. And if we have 2 pi, we'll have 2 pi minus 2 sine of 2 pi, which will roughly give us 6.28. So that means that our absolute max is going to come and be 6.96, and our absolute min will be at negative 0.68. So absolute max is 6.96. And to be very explicit, this was 5 pi over 3 plus the square root of 3 when you go ahead and plug in with your unit circle. And the absolute min is negative 0.68. Again, if you be very precise with your unit circle, this will be pi over 3 minus the square root of 3. Remember that our extreme values are going to be the y values. So yes, pi over 3 and 5 pi over 3 are where these occur, but they are not in and of themselves the absolute mins and maxes. They're just where those occur. We'll go through one more example. So say we want to go ahead and find the extreme values of this function on the interval 0 to 8. So when we're looking at extreme values, this is just basically another way to say absolute min and absolute max. So first we need to make sure we know what the domain of this function is, so that way we know we don't have anything to worry about. So because we have a square root, we need to make sure that for the domain of f, that x plus 8 is greater than or equal to 0. And so if we're saying this, this tells us that x has to be greater than or equal to negative 8, or in other words, that the domain is going to be negative 8 to infinity. The nice thing for us is that we're on the interval 0 to 8, so this means that over our domain, this will be fine. We're not interested in this anything outside of this interval 0 to 8. So now we want to go ahead and find our derivative. So again, if we go ahead and think of this as being 3x minus 18 times x plus 8 to the 1/2, what one could do is one could use chain rule on this to go ahead and get what the derivative will end up being. So I'll just kind of show us what we end up getting for the derivative. It'll be 3 minus 9 times x plus 8 to the negative 1/2 times 1. Or in other words, 3 minus 9 over the square root of x plus 8. So again, to find these critical points, we're interested in two things. We want to know where f prime equals 0 and where it doesn't exist. So we've got the derivative now, which is handy. So first we'll go ahead and set it equal to 0. So 3 minus 9 over the square root of x plus 8 equals 0. What we can do is we can move over the 9 over x plus 8, that's negative, make this 3 equals 9 over the square root of x plus 8, and then we can multiply the square root of x plus 8 over. So then we will get 3 square root of x plus 8 equals 9. We'll divide over the 3, and we'll get the square root of x plus 8 equals 3. Now, our next step will be to go ahead and square both sides to get rid of the square root. So when we square both sides, we end up getting x plus 8 equals 9. And so subtracting over tells us that x equals 1 will be one of our critical points. The next thing we want to do is look at where the derivative does not exist. So here our main issues are going to be the square root in the denominator. So we want to make sure this is not equal to 0. So it does not exist when the square root of x plus 8 equals 0, which will end up telling us that it does not exist when x equals negative 8. This is something that's in our domain. However, it's not in the interval we care about. So in domain, but not in interval we care about. We also need for this to be something where the square root has a non-negative number in it. So it does not exist when x plus 8 is less than 0. Which then tells us that it does not exist when x is less than negative 8. This is not in our domain anyway. So the only real critical point we have to worry about is x equals 1. So we'll make our table. And 1 may be our only critical point, but we still need to worry about the endpoints of the interval that we're given. So we're told that we have the interval from 0 to 8. So we'll want f of 1, which will be, again, taking the original function that we had up here. 3 times 1 minus 18 times the square root of 1 plus 8. And this will go ahead and give us negative 51. F of 0 will give us 0 minus 18 times the square root of 0 plus 8, which will give us, roughly speaking, negative 50.9. It's not as small as negative 51, so that's currently in the running for the absolute min. And if we look at f of 8, this is 8 minus 18 times the square root of 8 plus 8, which will give us negative 48. So all of this then tells us that the absolute min is going to be negative 51, and the absolute max is going to be negative 48. Again, this is over the interval 0 to 8, so we might have higher values, we might have lower values, but on our interval, this is the highest and lowest things that we'll have. Now, at the end of the notes packet here, I've got some trig identities that might be helpful to know depending on what ends up showing up on the WebAssign. So there might be some things where you have cosine of 2x or sine of 2x, and these are some formulas you can use to rewrite these.